coming. I'm going to tell you about some work that I've done looking at modelled GIS routes versus the actual data for people's journeys into work. Okay, understanding travel behaviour helps us to build good transport systems, efficient transport systems that work well. Of course, it helps us to improve our environment, cut down on CO2 maybe, and also be active, healthy people like we go here. I mean, the main reason for this is so that we can target interventions to improve our surroundings. Our environment around us influences this behaviour. There's been a lot of research that's looked into this. What's around you encourages you to behave in different ways. If you've got good provision here, good cars, then people use them. This is Cambridge Station, a bit crazy with cycles, but loads of people cycle. It's part of the culture there as well. Areas that aren't so nice discourage people from using their environment in certain ways. I mean, it might not be very nice to walk around this area here, well, I think that's quite amazing, but it might not be. And the implications from this, as I've alluded, environmental, air quality, healthy, or obviously the big drive at the moment is to cut down on obesity and prevent us looking like this on a drive to work. So we want to know where these healthy behaviours occur. Okay, so how can we find out where people are being active, where people are walking, cycling, etc. So using GPS, or God's parenting system, is a good way of finding out objectively where people are. And if you combine this with activity data, such as accelerometers, a bit like a pedometer really, but they monitor movement and speed, so you can estimate what people are doing in different locations. And as we've said, one example of this is to understand the daily commuting to work. It's something that most people of working age do twice a day, perhaps. So there's a big scope there to encourage people to perhaps be doing this rather than doing this. But the main thing is finding out what goes from where. But of course, with GPS, there's a whole host of problems. It's not that easy to get a hold of. It takes time. So if you're fitting up people with any kind of monitoring GPS system devices, it takes time to get this information. It takes a hell of a lot of money as well, from the time involved and from the equipment that we need as well, and the processing. Obviously, issues with error. So if you're fitting people with these, you might have issues such as low batteries, or they're not warm properly, or they take them off, or you get errors, you get scatter. And then, if anyone has dealt with GPS data, you know it just is a nightmare, because there's so much data there, and it's extracting that, and it's using software that can actually handle all that information. This is some software that's being designed is meant to improve creating, because I mean you get all this data, all this scatter. This Palm software is meant to match activity data with GPS data and manually and automatically extract routes for this information. But I've tried this, and for one route it picked up 92 trips. So I mean it's still not, we can't really use that for this sort of stuff. As I said, there's been a variety of research into this and how you get hold of this data, but no one's entirely cracked it because it's just such a complicated world. So the question that I want to ask is, okay, well, we know that that's really difficult. So our modelled routes, the use of a substitute, what are the problems with using modelled routes? Well, maybe what are the advantages? What are they good at picking up? And there's been a bit of work into this. So Panther et al. Looked into children's routes into work, but they made very simple assumptions on direct routes with no different directions or anything like that. Shortest route from point to point. And this research by Dalton et al. Has looked into they've actually compared the two GPS and GIS routes, but they looked at school children one day, 59 trips. So I mean they came up with the conclusion that distance overall doesn't make any difference in terms of the actual length of the route, but things such as busy roads could be interpreted differently depending on what type of route you use. So, I mean, the conclusion is that, well, there's a limited amount of empirical work here. So, I tested this using data from this Commuting and Health in Cambridge. It's a study into what they call a natural experiment in Cambridge, where they're evaluating the success of this new guided bus route. So the aim is they've got before and after data and see how people's behaviour changes, and if you can attribute this to a new transport system. And here's a picture of the bus running along this route here. And participants filled in various both objective and self-complete questionnaire and travel diaries. So we've used they were fitted with GPS receiver, but also the activity monitors, and various people did enhanced methods. They had heart rate monitors and other such things. But the stuff that I'm interested in is data that was collected in 2010 using the GPS. There were nearly 200 people that took part, but I've used data for 51 of these people based on a random selection. My aim was to obtain 50 modes, 50 trips per each of 6 modes of travel. So walking, cycling, car, bus, car plus walk, car plus bike. We had fewer people that walked and used car plus bike, so we didn't quite get 50 of those. But this is a total of 176 trips that I looked at. Okay, so the questions that I wanted to ask is, well, how well do these model routes reflect the actual routes that were taken? And how strongly are these differences dependent on the mode that people use? I.e., can we a model route's better for different modes used? And just something that I wanted to just look at very, very briefly in terms of how would this affect our conclusions using a model rather than the actual routes? How would it affect our conclusions on things such as energy expenditure and carbon emissions? Okay, so I went through this whole headache again of matching up, combining different types of data. We've got ITN data, OpenStreetMap data, local authority data, to put in those the information about public footpaths, etc. Did this in our friend ArcGIS, and I had 2 separate networks. So I had a car and a bike network. So one that I would use to model the routes for people that drove or took the bus to work, the other for people that cycled or walked. And then georeferenced home and work locations from data that they provided in the questionnaire from their postcodes. And to model this, I just looked at the shortest route between the origin and the destination. So the actual routes weren't quite straightforward, although I didn't spend months sorting out the road network for these. So, as I said, from the questionnaire, we asked people what they did in the last 7 days. So for each one of those days, I looked at what they did, the mode that they used, and extracted GPS data based on start and finish times for work. As I said, I've got the 6 modes of travel here. So this is the raw GPS that it came out. So you can see, here's the home, here's the work. A bit of scatter at the bottom. This is Addenbrooke's Hospital down here in Cambridge. And they've obviously done a bit of a loop before, or after they've got home. I'm not sure if this is the to or from journey. So I cleaned this. As I said, there's no automated software that can sort of rip out all of the nonsense from this. So I had to sort of just follow when they finished up at home or started from home, and then the same with their work destination. And then from this, because I was using 9.3, I could use horse tools and just link this up as the actual route that they've used. And from the routes that were taken, I buffered both of them so I could look at various factors. So the first was to look at the amount that the actual route overlapped with the model route. So you see this grey buffer here is the model route buffered by 50 metres. I tried this with 15 metres as well, and then the regression model that I did in the end, it made no difference other than walking became a significant mode, because a lot of the walk actual routes were off the road network, so they wouldn't be captured by them.
Got about 5 minutes.
Okay, good, thanks. Okay, so we looked at that. Compared the distance, just a crude distance measure. I looked at the amount of busy roads. Destinations, points of interest from point X, so we had leisure destinations, retail, food, education. I looked at if they went via anywhere, just by looking at the GPS data, such as at school, or if they went to the pub after work, or cafe, or whatever. Route directness, I looked at carbon dioxide based on DEFRA guidelines for average emissions. And then I looked at energy using the metabolic equivalent in terms of for different modes. So if you walk, you use X amount of energy, etc. So just a quick example. So here we've got the model route here, the black here, and then the actual route there. So this for a bike journey is 23.6% overlap on that. And then I compared the number of points of interest in each of the buffered routes. That's with a 100-metre buffer to capture the surroundings of the route. Okay, so ask the question, is this model behaviour? So in route length, for every mode, apart from walk, the routes were longer. You can see we've got, so car users, the routes were up nearly 50% longer. In terms of number of destinations, well, a bit of a mixed bag. Some routes, people would pass more points of interest. Some routes up to 50% less, such as the walkers that may be taking cut-throughs and things away from main streets. Then we've got the busy roads here, so car, they use much busy routes, and use motorways or whatever, go out their way to use a busier, faster route. In terms of distance, well here, this is a bit of looks a bit scary, this graph, but we're just comparing the difference between actual model distance to the mean. So on average, distance is 4.3 kilometres longer than what a model route would suggest. So I put this into a regression model. 16, I wasn't looking to completely predict the route, I was just looking to see the basic differences between the two. So the things that were significant were distance, mode, and if they went via anywhere. So 16% of the variance was explained by distance and mode, but when you put vias in, it explained a little bit more here. But individual and household predictors weren't significant in this, so it didn't matter how old people were, etc. That wasn't relevant. So the routes that were most accurately predicted were people that used car and walk to get to work. For routes that were longer, because if it's a shorter route, a small deviation makes a big impact on the overall distance, and as we've said, they didn't have vias. So this was looking at the overlap. So for bus users, the proportion of overlap was almost 50%. So they may not follow, bus routes may not always be direct, bit wiggly maybe, but I think they might sort of deviate then come back to the main direct route perhaps. And it's got very short confidence intervals, so it doesn't vary much. Car and walk on the opposite end of the spectrum, the least amount of overlap between the model and the actual. Walk had very, very big confidence intervals, so people don't, there's a lot of variance in terms of how people, the routes that people take when they walk in. So in terms of looking at the overlap, again I put this in a regression model using Stata, a logic model, because we're looking at proportion from a value of 0 to 1, so we need to put it in there. And the things that came out significant, the routes that were most accurately predicted from that, bus and walk journeys, not bus plus walk, bus and. So here we've got direct routes that are shorter with more destinations, and journeys that are made by older, healthier people. So here we've got some individual factors coming in. And I'm not going to go into, okay, here we've got just the overall conclusion between the CO2 and the energy expenditure implications. CO2 emissions would be underestimated by 26% if you just used the model routes alone. And energy expenditure, not for walkers, that wasn't significant, but for cyclists it would be about 7% underestimated, so is Boris having some fun there? Okay, so what? Why have I done this? Well, I wanted to see what we have to think about in the future when we're doing this. You need to consider mode, vias, road type, points of interest, these different factors, because it does vary according to what you're looking at. And as you can see, we came to slightly different conclusions depending on what our outcome is here. Are we looking at the distance? Are we looking at the difference in distance? Are we looking at the amount of overlap and concordance between those two routes? And we've got to be careful about the assumptions that we make here, the limitations, and I carried out the sensitivity testing on different buffers just to see if that would affect the overall model. So there are elements that can be under and overestimated using model group. And software, I mean, this might be the key for all of us. I mean, we've recently purchased Accession, which is a routing software. You can put your bus stuff in there, and this is only 800 quid for an academic license, so it's pretty good, really. And it means that you can use, it's like a version of Travelline, but you can change the assumptions that you make and that stuff into there. But I know there are more complex transport software packages out there, but they're probably slightly inaccessible. So ArcGIS may be the convenient option. Okay, well, thank you very much.